So, hello everyone. We're going to present the Lima driver status update. This is Vasily, this is Kernel, and I'm Erico. So, in a quick slide, what exactly is Lima? Lima is an open source driver, open source graphics driver for the Mali 400 and Mali 450 GPUs from ARM. And we're doing this over reverse engineering. And the driver got recently merged to Mesa and to the Linux kernel in the 19.1 and 5.2 releases. So some random facts about the Mali 400 and Mali 450. ARM claims it to be one of the world's most shipped mobile GPUs, and if you have any of these recent ARM SBCs, it's possible that you have one of these. It supports OpenGL ES 2.0. It has a tiling rendering model like many of the other mobile GPUs. It has two different cores, which means we have two different instruction sets and two different compilers, which we are going to talk about during the talk. So the Mali 400 and Mali 450 are kind of an old product by now. Most GPUs these days are doing the unified shaders, but we are having double work here because we have to support two different instruction sets. And it can support up to 8 pixel processing cores and up to 2 geometry processing cores, or the Vertex processing cores in the Mali 450. We don't have integer support, and that was actually a bit of a problem in the beginning of development. We have to lower everything to floating point, and that may cause some precision problems in some applications. So we don't have that. We do have an offline shader compiler available, which is a very good source for reverse engineering. Basically, you can throw some shaders there and change some values and use that to find out what the instructions are doing. And one of the problems with these GPUs is that there was never an open source driver for it, and many distributions decide to just not support these devices because there was no way to support it using just the blob driver or the kernel driver that we actually have the source for, but you do have to build an out-of-tree kernel driver. And nobody was willing to do that in the upstream distributions. And finally, I would just like to mention this for the record. The Mali 400 and Mali 450 do not have display controllers, so the GPU does not really have anything to do with the HDMI display or the LCD, so it's a completely different piece of hardware and a completely different driver. So if there's a problem with that, it's most likely not related to the actual GPU. So here are some examples of where you may find this device. So there are all sorts of, there are dozens of different vendors who are providing these ARM SBCs. They may come from Allwinner, from Rockchip, from Amlogic, or even from Samsung. And they range from $10 up. You can actually buy one of these boards, and apparently everyone has one of these boards and they want to support some sort of Linux desktop on them. And they've been patiently waiting for a long time to do that. And we also have some other more interesting devices, like, for example, the Pinebook, which was released not so long ago. And it could actually be a decent platform for a lightweight desktop, but because we didn't have the driver, it was not really that useful for that yet. We have some of the older Samsung phones that also have the GPU, and there are some sorts of mobile operating systems that people want to target for these devices, and they're also waiting for open source driver in order to do it. And even though the GPU is a bit old, we actually have devices to be released, like the PinePhone, which is going to probably rely a lot on the Lima driver. So yeah, the point is that even if the GPU is a bit old, it's still out there, and there are still devices that are recent that are using it, and there's still devices to come that are going to use it. So the effort actually started quite some time ago, around 2011, as far as I could track, with the original limadriver.org project, which Connor was part of, and it's great that he's still here with us. And that was the effort mainly from Luc Verhagen, which basically bootstrapped the entire reverse engineering drivers for the mobile ARM GPUs on ARM platforms. But the project kind of lost traction and died by around 2015. And by then we didn't have any driver merged to the mesa or to the kernel or any upstream project. So around 2017, Chiang Yu or Yuk started a new effort to port all of that code from the first reverse engineering project to an actual driver in mesa. And that was started in a project in GitHub, and eventually it was moved to a group in the Free Desktop GitLab. And that is actually the driver that we have today. So we have a lot to thank for him for restarting the project. It's too bad that he couldn't be here. He really should be here to present this talk because it's a lot of his work. And of course, a lot of the original project providing the most of the reverse engineering as well. So we still have a lot of code that is basically copy and pasted from the original project. And pretty much all of the reverse engineering that we have today, we have some of the documentation that come from this original project are basically still our reference for what we do today. Every now and then we find something that we didn't know before or some wrong assumption, but basically most of what we know about the GPU is because of the original project. So we have to thank a lot for that. So the Lima driver that we have today is a Gallium driver. It's in Mesa upstream. It uses the near compiler. It uses the render only or KMS arrow for display to interact with the other driver that is actually doing the display on the screen. And that puts us pretty much very close to what the other drivers in Mesa are, like VC4, the Etnaviv driver, or Freedreno. We actually reference a lot of these other drivers to see how we should be doing things, so we're pretty close to that. And we have two different compilers, which are the gpir and ppir. So we're going to talk about those, and I will pass the word to Connor to give us some more details about the gpir, the Vertex shader compiler.
Yeah, so the GP, the geometry processor, is the thing that runs Vertex shaders in the Mali 450, Mali 400 and Mali 450. It was designed a long, long time ago. So this is what the phone of the future from the original design sheet that described the Mali GP. And as you can see, it's aged quite a lot. But amazingly, things are still shipping using this. And when they designed this thing, I think to understand why it's so hard and why it took me like a few years to actually write a compiler, and ARM actually never wrote a compiler that fully worked for this thing. To understand like how this happened, how the disaster happened, you have to go back to when they were designing it in like 2004 or 2005. Their goal was, because again, back then, there wasn't, like mobile chips were pretty small, space was extremely limited. So their goal was to make it as small as possible and still handle what was the workloads that were common at the time, which weren't really that complicated. And also at the time, GLES 2 wasn't even a thing. So programmable shaders were not a thing on mobile yet. It was still a very new space. So they primarily designed it to do for like the old fixed function stuff and maybe some of the old like assembly programs, so that in the future they could do some more programmable Vertex shaders when that came along. But then when they tried to graft it onto GLES 2, it turned out to be a major, major problem because it just wasn't really set up for it. And the hardware itself is really simple. It has like 10 opcodes. It cannot do Vertex shader. It cannot fetch from a texture. There is literally no way to access main memory from the shader, so it can't even stall the pipeline. Like, this is like the simplest possible thing, right? That's as small as possible, and yet it's almost impossible to write a compiler for. And it was something that during the original project, I couldn't do it. I just didn't have the knowledge. So then now I came back much later after having done a lot of other stuff, and I figured I can do this as a side project. I can like actually finish what I started all of those years ago. And so to explain why what happened, I have to go back to some stuff that you may have learned in your Intro to CompArch class years and years ago and forgotten, which is how pipelining works. So this is your basic like 5-stage MIPS pipeline that you've probably seen in some textbook somewhere. You fetch an instruction, you figure out what to do with it, you read the sources, you execute this, you execute the add or multiply or whatever, and then you write back the results. And the instructions flow through this, so it's like, you know, a conveyor belt where each instruction is being done in parallel. And then there's, again, the classic problem that you probably learned about and forgot about, which is that while you're executing the read phase for one instruction, the last two instructions are in the execute and write phase. So if you ask for a register that was just written 1 or 2 cycles ago, it's not going to be there, or it may or may not be there depending upon, you know, vagaries of the hardware, but it's not something you can rely on. So this is called a hazard. It's pretty simple. The solution is pretty simple. You just directly output the phase, directly output, you know, the result of those stages, and you figure out at runtime, oh shit, I'm reading the result of an instruction that was written 1 cycle ago or 2 cycles ago, so I'm going to redirect it from the direct output, the output there. What ARM does is a little bit more sophisticated. They, again, wanted to save transistors, so rather than doing this on the fly like every other CPU does, they have these pipeline registers where you basically reserve, say, 2 registers to refer to the results of the last 2 cycles. And then the compiler has to figure out when this hazard would happen and would write this and uses these special pipeline registers instead. Here I'm using the carets to represent the pipeline registers because that's what our disassembler uses, but I have no idea what ARM does internally. So what does the execute stage look like in the Mali GP? You can do 2 multiplies, you can do 2 adds, you can do a table lookup and 1 miscellaneous thing per instruction. It's a very large instruction word architecture, so all of this happens in parallel, and it's all specified explicitly in the instruction set. The compiler has to decide which of these, when it's going to use these units. So and registers are extremely limited what registers you can read and write, because, again, they wanted to save transistors, and being able to read lots of different things at the same time is expensive. You can only read 2 vectors of 4 registers per cycle, and you can write 1 vector of 4 registers per cycle. And they do something that, again, they reused later, I think, for Bifrost, where the read ports and the execute units are kind of decoupled. So you specify for each instruction, I want to read register 1, and then I want to add component 1 of what I just read and component 2 of what I just read. And that's all well and good. And then, of course, they add the additional complication that you can directly read from the results of the last 2 cycles with these pipeline registers. So instead of reading component 1 of the register read, I can just directly read from the add unit 2 cycles ago, say. And this is all that information in a pictorial form because I think it's a little easier to digest than a bunch of words. These arrows represent the flow of data throughout the pipeline. You can see that you have these bypass things here, so that the result of all of these units can be fed again into the next 2 cycles. So it's pretty straightforward if you want to write a simple compiler for this, because it's designed to handle old vector programs. You just split each instruction in half because there's 2 adds and 2 mulls, and then you kind of schedule one part here, one part there, and then if there's a hazard, you just rewrite it to use the result of the last unit directly. But because they wanted to save transistors, again, there's a hard limit of 512 instructions per program, and this approach doesn't really let you use the resources very well because you can only read 2 VEC4 registers per cycle. And that, if you think about it, in most programs, you're not going to be adding and multiplying stuff from the same register at the same time. So you're going to leave half of your resources unutilized for most programs. And this means that you're going to run over the limit as soon as you start writing more complex shaders like people wanted to do when GLES 2 came out. So what did ARM do when they realized that their fancy new hardware wasn't going to work well with the spec that was being developed at the time? They came up with a hack. Most of those units are, so you can take those unutilized units, and rather than even if the, when you write something, the read is far enough away that you could use a register, instead take those unused units and thread, using the bypass network that was meant to avoid hazards, instead you thread the unit through. So every 2 cycles you have another move instruction, and then at the end, you can get from A to B without using any register reads or writes, only the bypass unit. And this is something that has never been done before or since, as far as I know. And it works, kind of. They kind of got it to work. This is from ARM's official documentation. So it turns out that there are some cases where this just doesn't work, because if you run out, let's say that you try to do this move threading, you split everything into scalars, you assume that you can use the bypass network to get from A to B directly, and then you find out that you can't. But maybe you ran out of register bandwidth, so you can't spill something to registers instead, and you can't thread it. You're screwed. And ARM never really figured out a way to resolve that situation. So we have this nice little note in there of documentation for the offline shader compiler. Sometimes it just gives up. And when Chang emailed me, of course, after he had restarted the project, he was like, hey, how do you write a compiler for this? And I had a suggestion of how to do it. He implemented it. It didn't work. It was too many. It didn't run into this problem that ARM had, but it made things too long, too many instructions, so even simple GeoMark2 shaders would overflow the 512 instruction limit, and it just didn't work. So then I was like, okay, I'll just implement it myself, right? This can't be too hard. And then here I am a year later, and it actually kind of works now, amazingly. We just recently got control flow implemented, which apparently made KDE work, which is pretty cool. Everything is wired up. The only thing that's not done is indirect accessing and spilling, which is a little complicated because of how ARM has these special address registers and a few design decisions about how it seems very like bolted on and added afterwards, which makes it hard to support in the compiler.
Yeah, so let's switch to the pixel processor core. And when you compare it to a geometry processor, it's actually quite sane. It's a lot saner, I would say, and it's a lot easier to write a compiler for it. So it's still a very long instruction world VEC4 architecture. Well, actually GP is scalar, but this one is VEC4. But some ops are only scalar. And yeah, there is a huge drawback of the pixel processor. So it supports only FP16 precision. So yeah, basically, it's not very good. It was okay for GLES 2, where you didn't have to support high precision, but it kind of doesn't work well on desktop GL. So ARM added a special path for loading varings that are coordinates of the textures. So there is a special path for it, and if you do that, you actually get 32-bit precision. But if you try to do any calculations with the sampler coordinates, it gets back to FP16. And yeah, some of Piglit tests fail due to insufficient precision. There is also another issue. It has only 6 VEC4 registers, but I guess they have more in silicon. Their site claims that it can spawn up to 128 threads. So yeah, I guess it's 768 in total in silicon probably. And there is also some pipeline registers, so they are not the physical registers. You can use them only within the single instruction. And if you do so, you can actually save a physical register in some cases. So what it can do in one instruction? Well, it turns out that a lot of things. So it can load one VEC4 of uniform or a temporary. It can load one VEC4 variant. It can sample a texture. It can also do 14 floating point operations. So it has one VEC4 addition, one VEC4 multiplication, one scalar addition, one scalar multiplication, and there is also one VEC4 by scalar multiplication and some ops like sine and cosine. And of course, it can store temporary or do frame buffer fetch. So this is the pipeline of pixel processors. We understand it. Of course, maybe it's not that accurate. Well, ARM folks maybe know better. Yeah. So for the compiler, so it was pretty straightforward to write a compiler for pixel processor, and we don't have this ridiculous limit of 512 instructions here, so we don't have to be as efficient as ARM compiler at the beginning, and we can get there eventually. So you can actually translate most of the near ops into pixel processor ops directly. But there are some, well, basically there is some exceptions for that. For example, we have to do to dance around with a variant that is a coordinate of the sampler, since, well, apparently in inner it's just usually an SSA or inner register, and it's we treat it as a special op in PPIR. Yeah. Also, we do some extra lowering in the PPIR. For example, we do duplication of all the uniform loads, since uniform can be passed directly to LEU nodes if well, if you do it in the same instruction. So basically, we duplicate uniform loads into the each user, and it appears that ARM compiler does the same, and ARM side claims that there is no penalty for reading the value from cache, and there is only one cycle penalty if you read it from memory. Well, depending on depending on the memory bandwidth, of course, if you share it with display and other stuff. Yeah, so basically when we, after we converted all the near ops into PPIR ops, we try to bundle them into the single instruction, and unfortunately our compiler is not that smart, and basically it's not aware of register pressure, and in some cases it may run out of the physical registers. Yeah. We'll have to fix it eventually. For register allocation, we currently use the one from Mesa, and if it fails, we try to spill. Yeah, and for code generation, there is not a lot of tricks. Yeah, I think I already covered this slide. So for the current status of PPIR compiler, most of near ops are implemented. Control flow is supported. We do support spilling with, well, let's say we do support spilling, and it can deal with quite complex shaders. Yeah, I'll pass the word to Erico.
So, of course, we also have the kernel part of the Lima driver. It's already merged in 5.2. It's a gem driver. It uses the DRM scheduler. It uses Prime to communicate with the other driver that will do the display part. So that puts us in pretty much like the other drivers for the ARM GPUs are, like the VC4 or the Etnaviv driver. We actually look a lot into that to see how we should do things here as well. And with the Prime display, we actually have it working on the all-winners and for platforms, Rockchip, the Amlogic platforms, and Exynos. They should all be working. And since the driver was merged in 5.2, it actually didn't change that much. We do have a couple of bug fixes and some things that changed in the DRM MISC next branch, and then you had to fix it before it got merged into the actual released kernel. But in the kernel driver, it's actually looking good. We may have some changes for 5.4, but overall, it should be fine to use a recently released kernel. So right now, what works? Actually, quite a lot. Maybe this is a bit outdated. So the mesa driver is actually evolving pretty fast. If you have a copy of mesa that you built last week, that's too old already, because this week's version might have fixed a lot of applications already. So basically, KMSQ was the first thing that was working when we had the driver merged. We have reports that Kodi works. We have some users of MidTV also reporting that it works. MPV for video. Piglet, many of the tests are actually working at this point. We did work a lot based on Piglet in the beginning. And yeah, with restrictions, but I guess most of the low-hanging fruit is actually fixed at this point. The AQP runs, but we didn't start to clean up the failures yet, but it does work. GL Mark II, most of the demos work. I think a couple of them crash because they try to use a buffer that is located statically with the fixed size that is not enough for some of the demos because they use a lot of geometry, and that's only a thing on these benchmarks anyway. So not all work, but most work. Quake 3 Arena should be working with the GL1 renderer, not GL2, because, well, maybe it does now, I don't know.
I haven't tried it.
Yeah, well.
I'm not gonna do that.
So, yeah, no. So X should be working at this point since we got the control flow supporting the PPIR that resolved one of the glamour shaders. So it should be working. That doesn't mean that all desktop environments work, but at least X works with the glamour. Sway and Weston, I think the situation is a little better in the Wayland compositors at this point. And apparently KD also works now that you have control flow in the gpir. So yeah, for a long time, we were pretty much working on the Piglet tests. That means we were basically trying to clean up the Piglet tests, and that was a bit frustrating maybe for users because it didn't seem like we were trying to make the applications that end users actually wanted to run work. But at the same time, we knew that there were a lot of things to be fixed, especially in the compilers, and that's why we were working on the Piglet tests. But yeah, at this point, I think we kind of moved on from focusing so much on the Piglet tests. Some of the demos application work, but many of them are still unsupported. So at this point, I guess I would say that the driver is not ready to be in production, but it's getting close to that. But yeah, I guess we can say that the driver should be in production. Yeah, that's all. But it's fast getting more and more applications working. Apparently, Android mostly works. Didn't try it myself. I don't know if any of us actually tried it, but we have reports from users trying to do that, and there are only some rendering artifacts. So we have a group in the GitLab free desktop. That's what you use for some of the project documentation, but of course the merge requests and issues could go to the upstream project. Actually, the Linux and Mesa repositories in that project are deprecated. It should just go to the Mesa one now and upstream Linux. We do have a mailing list that you can use to reach us, and the IRC channel on Freenode, #Lima, is actually fairly active. I think we're always there. And of course, we have a demo if everything will work.
Hi, I'm very impressed with the work you're doing. I worked at ARM developing the driver you're replacing. Good stuff. Are you planning on supporting features that the binary blob doesn't support?
I guess I'll try to answer that. So we do support one feature that binary blob doesn't support. That's rectangular textures. We just occasionally discovered how to do that last week, I think. Yeah, and beside that, I'm not sure. We can try to poke some bits, like to try enabling 3D textures, since apparently hardware supports it. But going further, well, if ARM offline compiler doesn't expose something, we don't have a reference to reverse engineer. Yeah.
Yeah, I mean, all we can do is just try all the bit patterns until something works out, right? There's not like, it's finding the magic thing when it's not there is like really hard. And also, there's not a ton more, I think, that we could do that they don't support. There's 3D textures, obviously, and rectangular textures, but I can't really think of anything else that isn't in the spec, the original product spec somewhere that they never really supported.
So looks like in Glass 2 you can't write depth from fragment shader, but Connor and Luke did some reverse engineering of MBS format, and apparently there is a field that is set when shader writes depth, but we just don't know how to do that.
Yeah, and I think there's some weirdo like call and return instruction too. I don't think it's going to be too useful if you want to have an actual stack in your fragment shader.
Question. I think it was one of the first few slides. It was about Mali 400, 450. I think one of the things that was mentioned there was, I think it said there is a out-of-tree device driver, and I think the presenter mentioned that you couldn't really use that. So what is that driver? What does it do? What is the issue? Maybe just from my own experience, I deal with VIA Technologies graphic stuff, and from my experience, there's about like I think I know at least 5 different implementation. OpenChrome is just one of it. So I sometimes have to go look at some other code written by some other people to learn about the hardware and all that. So I'm just wondering if it's like a situation like that.
Well, it's first of all, it's only the kernel driver, which is like a tiny percentage of what you need, and it doesn't use any of the standard kernel stuff that Lima uses. It's only written for the proprietary driver, and at this point, they're never going to change the proprietary driver to use Lima's because they've moved on, right? Even though people are still selling devices using this stuff, I don't think they really care enough. So yeah, it's there. You can compile it. It's open source, but it's not like it's a dead end. It's not something that actually uses upstream in any way.
So if I were to follow, so is it? But is there some like can you learn something from that? Is there something?
I mean, yeah, absolutely. There's probably a few things in there that aren't like implemented yet in the kernel, but not a lot. So yeah, when the kernel driver was written, like yeah, they referred. You referred back to this, back to that driver, but it's not useful for anything other than a reference.
Okay, thank you.
Also, this driver that is available doesn't use the standard interface that all other drivers use. It uses just the dev Mali device node, which Mesa can't really make use of, so we can just use that for now. We'd have to just change the way we interact with the kernel. Any more questions? So let's do the demo now, if you can.
I'll try. I'll do my best.
So it's not GLX gears.
No, it's not.
Yeah, so this is the. There's even sound. Yeah, so. Yeah, so maybe if you want to see the demo more closely, you can just come and talk to us in the hall. And if there are no more questions, I guess that's it.